So the simulations that we're going to be discussing will, I hope, all have resolution better than 100 parsecs physical resolution, which we hope will be enough to begin at least to resolve star formation in galactic disks. The comparison of simulations is motivated by recent improvements in hydrodynamical simulation codes, the availability of millions of CPU hours for such simulations on high-performance computer systems, and the increasingly rapid acquisition of observational data on galaxies both nearby and out to very high redshifts. And we've, of course, been hearing about that at this meeting. The discussions today and over the weekend will consider the current results and performance of various simulation approaches. We want to compare simulations of the same cosmological initial conditions by different codes to each other and also to relevant observations. This will help advance the state-of-the-art of galaxy simulations and the understanding of the key astrophysical processes that control galaxy formation and evolution, including the flows of baryons into and out of galaxies, feedback from stars, supernovae, and massive black holes, and the impact of baryons on dark matter structure and substructure. We will try to model consistently similar recipes across codes rather than allowing complete freedom in implementation. We'll also discuss initial conditions for a range of galaxy masses, not just the Milky Way mass simulations that much earlier work is focused on. So this is from a text that a number of us discussed, Piero, Ramon Tessier, Lucio Meyer, and others. And I hope that this does represent a consensus here of what we're hoping to do. So what I want to do, as Piero said, is start with a word from our sponsor, which is the University of California High Performance Astro Computing Center, and then talk a bit more about the goals of this project and the organization of this workshop and of possible follow-up meetings, and list a bunch of choices that we need to make, but none of which have been made and are all up for discussion here. So this is the website for the High Performance Astro Computing Center. What happened was that in late 2009, there was a competition in the University of California. A number of the long-standing multi-campus research units had to recompete for funding from the system-wide University of California. And there was an opportunity to propose new ones. And it was pretty obvious from the call for proposals that a proposal that mentioned both high-performance computing and astronomy was likely to do well. And so I crafted such a proposal, and I was told it ranked second of all of the proposals submitted, which was like 100, and it was funded. There were two other proposals that were funded that had to do with astronomy. The Center for Galaxy Evolution proposal submitted by James Bullock, and also a proposal submitted from Berkeley emphasizing the gamma ray astronomy and underground detection of dark matter from Bernard Satellite. So of the 20-some projects that were funded, 3 of them actually were in astronomy. We came across pretty well. The result is that these organizations each get about $350,000 a year for a minimum of 5 years, so almost $2 million. And it's unrestricted money, there's no overhead, and that's what's allowing me to fund things like the Galaxy Workshop, a little bit of subsidy for that, but especially subsidizing this meeting starting now. And I'm glad that I've been able to help some people who otherwise might have had trouble coming by paying their transportation and lodging expenses. Anyway, HiPACC does lots of other things. Besides the website, this is sort of the goals of HiPACC. I'm not going to read it to you. This will go up on the web and you can read it. And of course, these things are also linked to the website. What it says is that we want to foster the interaction of the programs on all the University of California campuses in computational astrophysics and astrophysics in general, and also the 3 Department of Energy laboratories that we're affiliated with. That's Lawrence Berkeley Laboratory, Lawrence Livermore Laboratory, and Los Alamos National Laboratory. And we also do a lot of outreach, educational materials, publicity, our website, and we did a boot camp for journalists on computational astrophysics, and 20 of the top science journalists from Science, New Scientist, Discover, National Geographic, I mean, lots of magazines, TV shows, etc. were here, and we had faculty from across the system entertaining them, talking about projects in computational astrophysics. This is the leadership of HIPACC. I'm the director. Peter Nugent from Lawrence Berkeley Laboratory, he's the group leader for computational astrophysics, is the northern co-director or coordinator. Mike Norman, who is the director of the San Diego Supercomputer Center, and of course the founder of ENSO, is the Southern California director. And there's a council consisting of representatives from each campus, and that includes both observational astronomers like Sandy Faber and computational astrophysicists. And I think you've had a chance to meet the staff, one of whom is here, Nina McCurdy. And you've been dealing with Sue Grasso also. We have calls for funding for University of California affiliated people. Sorry if you're not affiliated with the University of California. You're not eligible for these funding things. But we have also funded conferences that have involved lots of non-University of California people. So there are 2 opportunities a year for calls for proposals. And a number of the people here have submitted proposals and been funded. We also do subsidize annual conferences both in Northern and Southern California, and every summer we have a summer school on some aspect of computational astrophysics. The 2010 summer school was here at UCSC, and it was on galaxy simulations. The 2011 school was in Berkeley, at Lawrence Berkeley Lab and on campus, directed by Don Kaysen and Peter Nugent, and it was on computational explosive astrophysics. In other words, supernovae, gamma ray bursts, and things like that. The one that we just had this summer was in July at the San Diego Supercomputer Center, and it was on astroinformatics. One of the features of our summer schools has been that all the students get accounts on a relevant supercomputer. And the codes are all put there, and there are afternoon hands-on sessions every day where the codes that are described in the morning can actually be used by the students that very afternoon with a lot of help from the people who wrote the codes and various other people. So at the summer school in July, the relevant machine was the new Flash Gordon computer that just went into operation in February of this year at San Diego Supercomputer Center. It is not one of the most powerful computational engines. What's remarkable about it is that it has 300 terabytes of flash, and you can allocate up to 10 terabytes of flash for an individual compute node. So this allows analysis of big data sets in an extremely easy way compared to what we usually have to do, which is to load in little pieces and worry about edge effects and so on. Anyway, all of the talks at the summer schools are recorded, and they're up on the web in both the slides and also the videos. We've also been doing the same thing with these galaxy workshops. So this was another one of our conferences. It was called The Future of Astrocomputing at the San Diego Supercomputer Center in December of 2010. This was the Galaxy Workshop last year here. I've already mentioned this boot camp. There's this workshop which is going on right now, and of course the simulation comparison project, which we're just starting now. This was the picture that we just took yesterday. There were several versions that, of course, were taken. There's always somebody whose head is hidden, and at least there's one. I think that may be Adi. Yeah, really unfortunate, because Adi Zolotov had the greatest role in actually planning the organization. So, but actually, your head was hidden in all 3 pictures. No, it's true. We could use Photoshop. We could use Photoshop. So, Nina, if you can figure out how to do that. So now, as everyone here no doubt knows, there are earlier examples of simulation comparison projects. One was the Santa Barbara Cluster Project, which resulted in a 1999 paper It started and then concluded with workshops at the Institute for Theoretical Physics in Santa Barbara, now known as the Kavli Institute, led by Carlos Frank. I was not involved in either of those, and so I guess that's why I was asked to review the paper. But in any case, I think it was a very useful exercise. The conclusion was that the codes pretty much agreed at the outer parts of galaxy clusters, and they all agreed with each other pretty well in the inner parts and disagreed violently with the observations. So a lot was learned. There's recently been this paper called the Aquila Comparison Project, the effects of feedback and numerical methods on simulations of galaxy formation, led by Cecilia Scannapieco, with a number of the people in this room involved. These simulations mostly used gadget smooth particle hydrocode and had force resolutions of the order of a kiloparsec, with dark matter particle masses larger than 10 to the 6 solar masses, and gas particle masses larger than about a half times 10 to the 6 solar masses. The one adaptive mesh refinement code used in these simulations, Ramses, Roman Tessier, of course, is here, was run with relatively poor force resolution for Ramses of 260 parsecs co-moving, which meant, of course, that at redshift 9, it was 26 parsecs physical, which is quite good, and a particle mass of only 0.2 times 10 to the 6 solar masses, which, again, was better than any of the other ones. At these resolutions, however, all the key physics of star formation and feedback is subgrid, and it is therefore not surprising that there were large code-to-code variations in the size, morphology, and stellar and gas masses of the simulated galaxies starting from the same initial conditions, and rather poor agreement with observed galaxies. The success of recent higher resolution simulations such as Eris, which we're going to hear about in detail and probably everyone here is familiar with, in matching observed galaxies encourages us to hope for progress with the high resolution simulations that will be discussed here. So this is the abstract of the Scannapieco et al. Aquila paper, and the various runs had the same initial conditions and tried to do the latest published model of gas cooling, star formation, and feedback, but none of them did radiative feedback. It was all supernova. Despite the common halo assembly history, we found large code-to-code variations in all of these things. Most codes led to an overly massive galaxy, smaller and gas-rich, that is with too many stars, than typical spirals with a massive bulge and declining rotation curve, again, contrary to observations. Developing feedback algorithms that can effectively regulate the mass of a galaxy without hindering the formation of high angular momentum stellar disks remains a challenge, was the conclusion of the abstract. This was the table of the codes and the resolutions, and for all of the codes except Ramses, the softening was 500 parsecs or worse, typically fixed at a redshift of 3 or so. So, in other words, stellar disks which have scale heights of 100 parsecs were not being resolved, especially when you consider that the stated resolution should always be multiplied by some factor like 2 or 3 to get the true resolution of the code. So most stars form in galactic disks, so it's essential to resolve disks, and the scale height of the Milky Way disk, at least in O stars, is only 100 parsecs. So that's the scale that you have to do better than in order to really be discussing star formation and not putting it all into subgrid physics. So this is our calendar. The kickoff meeting for the comparison project is now. What we've been discussing is that we certainly don't want to wait a long time until we start comparing simulations, or at least our progress in setting up simulations. So roughly every 2 months, I hope that we can have at least a telecon or a web conference, maybe a serious web conference where we actually start to show each other results within about 6 months, so early next year, January or February. And in summer of 2013, we plan to have a summer school on galaxy formation, on star formation. I have galaxies on my mind. Here at UCSC, led by Mark Krumholtz, and including at least some of the people who have put a lot of effort not just into stars, but into understanding planet formation. So we're sure that we'll have a huge number of people applying for that. So the dates that we've adopted for that are July 22nd to August 9th. There's going to be a conference the previous week, ending the previous week, in Heidelberg on planet and star formation. And many of the people who will be at that conference are going to be coming here as either students or lecturers at the school. So I think those dates are fixed. The obvious date for next summer's Galaxy Workshop would be immediately following, so August 12th to 16th. And that means that we'll finish the Galaxy Workshop before schools that try to put in a full semester before Christmas start. Those typically start the third week in August, so if we have the Galaxy Workshop the second week, we can have it here. Then we could have the follow-up conference for the high-resolution Galaxy Simulation Comparison Project in either the immediate following week or 2 weeks or 3 weeks. If we went 3 weeks, that would mean we would overlap Labor Day, which may not be a desirable thing. Now, I wrote a proposal with the help of Piero, Romain Tessier, and Luciano, asking the Santa Barbara Kavli Institute for Theoretical Physics if we could use their space for a follow-up workshop. And what they said was, yes, sort of. So there's 20 spaces available for desks and computers and so forth, but they're not giving us any subsidy to help with local housing or travel. We had hoped that I said I would co-fund it with them with HIPACC funds, and they basically said, no, you're going to have to fund the whole thing. So Piero and I were discussing just having it here, because then we don't have a limit of 20. We're more flexible on dates, and it might make a lot of sense to do it right after the Galaxy Workshop. In any case, all of these questions are up for discussion, and I just wanted to let you know that that's what the possibilities are. So I've now covered the first 4 items. What I wanted to do was just discuss the choices to be made here. So I'm not going to spend any more time telling you what I think the right choices are, and just tell you what I think the questions are. And then I think later today and tomorrow, we're going to discuss all these questions. So one question is, what initial conditions to simulate? We want to have galaxy masses at redshift 0 covering a wide range. Partly because there's data on a wide range, partly because simulations that try to simulate a typical massive elliptical 10 to the 13 solar mass halo at redshift 0 may not finish, in other words, to redshift 0 or anything near redshift 0, even in a year's computer time. And in any case, simulating a galaxy like that without some serious attempt to include feedback from supermassive black holes at their centers isn't going to be very realistic. So what we want to do is have a wide range of halo masses corresponding to a wide range of galaxies, and have codes that will at least manage to get to redshifts that are low enough to compare with a lot of observational data within about a year. And of course, for each one of these, we want to have at least some choice of initial conditions with different merging trees. So you're going to see that using Oliver Hahn's music code, you're going to be shown examples of initial conditions and complete merger trees to redshift 0 for all of these masses, and with a choice of a relatively quiet merger history or a relatively violent merger history for each one. So there'll be talks later today and especially tomorrow and Sunday that go into those. What astrophysics should all groups try to include? Of course, every code is going to implement the astrophysics differently, and what I think we should do is have a set of astrophysical processes that everybody should agree to include, and then, of course, there'll be a bunch of optional ones, and nobody can be asked to simulate something that their code doesn't do. At what redshifts to compare simulations, and also how to compare the simulations. And I think what we want to do is compare at many different redshifts, starting at fairly high redshifts, and we want to have a set of tools available that will allow comparison to be done in as similar a way as possible. And fortunately, the YT toolset, which is a remarkable achievement by Matt Turk and his many collaborators, is being made available to be used with essentially every version of the different simulations, including SPH and the adaptive mesh refinement codes. And then finally, and Matt's going to tell you about that. And then finally, next year we want to have these follow-up meetings, and as I said, we have to decide when and where and how long that meeting should be. So these are the people who I know of who are here or who will be participating remotely. And actually, one person I listed as being not here, Tom Quinn, but fortunately he is. Anyway, the main thing to say about this is that all the main codes are represented. And in many cases, these people are just a fraction of the people who are going to be doing the relevant simulations, I think. So that's the end of my talk, and I think I've stayed within the time. And now I think we're going to hear from several of the people about more details about what they've been doing.